Good morning. I am Dr. Neeti Maheshwari, Assistant Professor, Applied Science and Humanities Department, Ajay Kumar Garg Engineering College, Ghaziabad. In the last class, I was taking the electrochemistry part, and in continuation with that part, today I am going to discuss about the Gibbs-Helmholtz equation. Now, this Gibbs-Helmholtz equation is a thermodynamic equation which is used for calculating the changes in the Gibbs free energy of any system as a function of temperature. And this equation has been named after Willard Gibbs and Hermann Helmholtz. And the definition of the Gibbs function, it is enthalpy, which is given by capital H, is equal to G, which is the Gibbs free energy, plus entropy, capital S, multiplied by temperature. So, here the enthalpy that we have taken in this equation, it is given by, this enthalpy H is given by capital U, which is the internal energy, and plus pressure and volume. So, pressure multiplied by volume. If we take the differentials of each definition for finding the changes, small changes in H and G, then using the fundamental thermodynamic relation, which is always true for reversible or irreversible processes, then a small change in the internal energy is given by TdS, that is temperature multiplied by very small change in the entropy minus pressure multiplied by very small change in the volume. So, this equation is valid for very small changes. Then here the S is the entropy, V is the volume, and the minus sign, it is due to the reversibility, in which the change in the internal energy will be equal to 0. So, work other than pressure volume may be done and is equal to minus PV, and it leads to the reverse form of the initial fundamental relation and forms a new equation which gives that very small changes in the Gibbs free energy dG is equal to minus SdT plus VdP. Now, this equation gives the Gibbs free energy for a closed system when a system undergoes reversibly a change in pressure as well as temperature. And if in this equation, if we keep pressure constant, that means changes are taking place when changes in dP is equal to 0, that is isobaric conditions, then this equation, changes in the Gibbs free energy at constant pressure is given by minus SdT, and the entropy, it can be calculated as minus dG by dt at constant pressure. Now, we all know that Gibbs free energy is equal to enthalpy minus temperature into entropy. So, putting this value of entropy in this equation, we get that G is equal to H plus T multiplied by dG divided by dt at constant pressure, changes in Gibbs free energy with respect to temperature at constant pressure. And the variation in the Gibbs free energy, delta G is equal to delta H, that is the changes in the enthalpy, plus T del delta G divided by dt at constant pressure. Now, this equation is known as the Gibbs-Helmholtz equation, and we can determine these thermodynamic parameters with the help of EMF. By the value of capital E, we can determine the values of these three thermodynamic parameters, that is delta G, delta H, delta S. Now here I am taking first the determination of delta H with the help of rate of change of EMF with temperature. Now delta G is not only equal to delta H minus T delta S, this delta G is also equal to minus NFE, where this is the electrical work done by the system. Since work is being done by the system, therefore there is a minus sign, where N is the number of electrons, capital F is the Faraday's constant. Now Gibbs-Helmholtz equation says that delta G is equal to delta H plus T del delta G by dt at constant pressure. Putting the value of delta G as minus NFE in this equation, we get delta H is equal to minus NFE plus T del NFE divided by dt at constant pressure. If we take minus NF as outside common factor, then this equation becomes delta H is equal to minus NF E minus T del E by del T at constant pressure. Similarly, here delta G is equal to delta H minus T delta S. As a result, we have already calculated that the entropy, variation in entropy delta S is equal to minus del delta G by dt at constant pressure, which is equal to NF. Instead of delta G, we can put minus NFE. So minus minus is going to be plus. So NF del E by del T at constant pressure. So if we know the EMF, we can calculate the values of delta G, delta H and delta S. I have taken one numerical. Now in this numerical, it says that the EMF of the cell, this is the cell, cadmium and silver cell involving the reaction. This is the reaction cadmium plus 2AgCl, it is forming cadmium chloride, hydrated cadmium chloride plus 2Ag, silver solid is being formed, and the EMF of the cell is 0.6753 volts and 0.6915 volts at two different temperatures. One I have taken as 25 degrees centigrade and the other is 0 degrees centigrade respectively. Now we have to calculate the values of delta H, delta G and delta S at 25 degree centigrade. Now for the calculation part or the solution part, first we can calculate the variation of EMF with respect to temperature at constant pressure. Now here del E by del T at constant pressure will be equal to variation of EMF at two different temperatures. So the value of EMF at higher temperature is 0.6753 minus the value of EMF at 0 degree centigrade divided by the variation of the temperature, and the temperature variation, whether we take it in the centigrade or Kelvin, degree Kelvin, this variation is of 25. 25 minus 0 or 298 minus 273, it is going to come out to be 25. So here this is the value for del E by del T at constant pressure. Now at 298 Kelvin, because we have to do different calculations at 25 degrees centigrade, this enthalpy, variation in enthalpy is given by minus NF E minus T del E by del T at constant pressure. So this can be given as, since the number of electrons involved in this equation are 2, so N is 2 and Faraday is 96485 minus, we have to take the EMF at 25 degrees centigrade minus 298, and this value we have already calculated. On putting these values, now we can calculate the value of delta H to be this. So, this is the value for delta H. Then once we have calculated enthalpy, we can calculate the Gibbs free energy by a simple equation. Delta G is equal to minus NFE. Since EMF is given at 25 degrees centigrade, simply multiplying that value with the F and number of electrons, we are going to get the value of delta G. So, here we have calculated the value of delta G. Similarly, now since we know delta G and delta H and temperature, we know to be 298 Kelvin. So, since we know the 3 other parameters, so we can easily calculate the value of delta S. So, here in this equation, we can calculate the value of minus delta S by putting the values of delta G, delta H and temperature as 298. So, minus delta S come out to be this, or delta S will be equal to minus 0.1254 kilojoule per Kelvin. So, in this manner we can calculate the values of enthalpy, Gibbs free energy and entropy. So, by knowing the EMF, we can calculate the thermodynamic parameters, and this is the application of finding the EMF or relating the EMF to the thermodynamic parameters. Next topic that I am going to discuss today is battery. Now, a cell, simple cell, it is made up of a single electrode, cathode and a single anode. But when 2 or more such electrochemical cells, they are electrically interconnected, each of which contains 2 electrodes, and then there is an electrolyte, then they form what we call as battery. In everyday usage, battery is also used to refer to a single cell. There is no battery design which is perfect for every application. For different applications, we have to use different kinds of batteries. Now, the types of batteries, coming to the types of batteries, batteries are of 2 types, primary batteries and secondary batteries. Now, the primary batteries are those which cannot be recharged and they are only for one time use. So, the primary batteries, they are non-rechargeable and they are meant for the single use and meant to be discarded after use. Since they are only for one time usage, therefore, they are less expensive. And for ordinary gadgets like torches, watches, toys, we use such types of batteries. And commercially, many such batteries are available like Leclanche cell, alkaline cell and the lithium cell. Coming to the secondary batteries. Now, secondary batteries are those which are rechargeable, which we can use many times. They undergo various cycles, a number of cycles of charging and discharging. And after every use, the electrochemical reaction could be reversed by external application of voltage. And this cycle we keep on doing till the capacity is lost. Capacity of the battery is lost. So, these cells, they are rechargeable and reusable. And a combination of all the reversible electrochemical cell gives secondary batteries. There are different kinds of secondary batteries which are available like lead acid cell battery or the nickel cadmium cells or the lithium ion cells. Now, today I am going to discuss about lead acid cells or the lead storage cells. Now, what are the storage cells? Cells or the batteries which can function as both, cells which can function as both voltaic cell as well as electrical cell. So, a voltaic cell is the one which produces electric current by the redox reaction, and electrical cell or electrolytic cell is the one which utilizes the energy of an external source to bring about the changes. So, this battery, it works as a storage cell. Now, in the case of lead acid cells, the anode, it is made up of metallic lead, and the cathode is made up of lead dioxide, and the electrolyte or these two electrodes, they are dipped inside the solution of a dilute sulfuric acid. So, that mixture is around 38% by weight of the aqueous sulfuric acid. And this lead acid batteries, they have the applications in the automobile industry and the construction equipment and in the standby and backup systems. Now, these lead acid batteries, they are used mainly for engine batteries, the car batteries. These cells, they represent over half of all the battery sales. Some advantages are their low cost, long life cycle and ability to withstand mistreatment. Again, they can perform good in high or low temperatures. There are certain problems also with these batteries, that if the cell voltage exceeds 2.39 volts, then the water, it breaks down into hydrogen and oxygen, and it may lead to the explosion. And the another problem may arise from the fumes coming from the acid solution, which may also have an effect on the area which is surrounding the battery. But these problems, they are mostly solved by sealing, and this sealing in reality is only valve regulated and allow hydrogen and oxygen recombination using catalytic recombination. They can convert these gases back into water, achieving about 85% efficiency at best. So, in these batteries, the water lost, it becomes very insignificant, and there is no need to refill from the entire lifetime of the battery. And this cell is also designed to prevent corrosive fumes coming out from the battery. Now, here I have taken a diagram which is showing the arrangement of the lead acid battery. So, here the negative electrode is made up of lead. So, here you can see the negative part, these are the lead, and the cathode, it is made up of lead dioxide. So, these are the lead dioxide. Both lead and lead dioxide, they are arranged in parallel. So, these different cells, they are arranged in parallel and they are dipped inside the solution of dilute sulfuric acid. So, the active material, the material in this cell which takes active participation in the chemical reaction, that is during the absorption or evolution of electrical energy, that is during charging or discharging, that is they are called the active material. And here the active materials are the lead dioxide and lead. So, lead dioxide, it forms the positive active material, that is the cathode, and the lead, it forms the negative active material, that is the anode. And the third active material is the dilute sulfuric acid, which is used as an electrolyte. Now, separators. Now, these various cells, they are separated from each other. These cells, they are separated from each other, and these separators, they are thin sheets of non-conducting material which is made up of chemically treated lead wood or the porous rubbers or mats of glass fibers, and these thin sheets, they are placed between the positive and the negative electrodes to insulate them from each other. Battery terminals. A battery, it has two terminals, the positive and the negative. The positive terminal has a bit diameter more in comparison to the negative terminal. Now, coming to the chemical action during discharging. When the cell is full discharge, then the anode is of lead peroxide and the cathode is of metallic lead or the sponge lead. When the electrodes, they are connected through a resistance, the cell discharge and the electrons flow in a direction opposite to that in the charging. So, when the cell, it behaves as a voltaic cell, it is said to be discharging. Now, in this case, the different reactions that are taking place during discharging. Here, first of all, the lead anode, this lead, it loses electrons. The lead which is present, it loses electrons to form lead plus 2 and it releases 2 electrons, and these electrons, they move from anode towards the cathode where these electrons, they are accepted by lead dioxide, and this lead ion, it combines with these lead ions, they combine with the sulfate ions to form the precipitate of lead sulfate. So, when these lead ions, they combine with sulfate ions, they form the precipitate of lead sulfate. So, here, since the electrons are being released, therefore, oxidation is taking place at the anode, and the overall reaction will become lead is going to combine with sulfate ions to form the lead sulfate, plus it is going to release the 2 electrons. At the cathode, the reduction is going to take place. Here, the lead dioxide, it is going to accept the 2 electrons. Here in the lead dioxide, this lead is present in the +4 oxidation state. So, lead undergoes a reduction from +4 oxidation state to +2 oxidation state, and this lead dioxide, it accepts the electron, and in the presence of sulfate ions, again it is going to form the precipitate of lead sulfate. And if we see the overall reaction, then lead, it combines with lead dioxide, and while accepting, because sulfate ions are being formed, therefore H plus are also going to be formed. Then H plus and sulfate ions, they combine to form 2 PbSO4 plus water, and in this reaction they release energy. Energy is being released in this reaction. Now, when the cells are fully discharged, so now they have to be recharged by connecting it to an external electrical source. Now, the cell is going to behave as an electrolytic cell. Now, the lead acid storage cell, it gives an EMF of 2 volts. So, after being discharged, they have to be connected through an external source with an EMF greater than 2 volts for its charging. So, a lead acid battery which is consisting of 6 cells will give 12 volts, and that containing 12 cells will give 24 volts. During use, both the electrodes of lead storage cell, they get coated with the precipitate of lead sulfate, and the sulfuric acid gets diluted. Its density decreases to about 1.1. When both these electrodes, they get covered with the lead sulfate, then the reaction stops, the cell stops giving the electric charge, and then we say that the cell, it's said to be dead or it is discharged. So, for recharging of this discharge cell, the lead of the anode and the lead dioxide of the cathode, they are completely converted to lead sulphate. The water which is being produced in the reaction, it dilutes the sulfuric acid. Now, in these conditions, the cell is not able to supply any electric charge, and the discharged lead storage cell, it has to be recharged by passing a direct current through the external source. And this direct current, it reverses the reactions, it brings the reactions in the backward direction again and converts the lead sulphate back to lead and lead dioxide on the respective electrodes. Now, during this charging, when we connect this storage cell to the external cell, the negative electrode of the storage cell is connected to the negative of the DC source, and the positive electrode of the lead acid storage cell is connected to the positive of the DC source. Here, so these are the reactions which are taking during the discharging. When it discharges, it produces this, and while charging, the reactions they become, again we get both lead and lead dioxide. So, here I am showing the diagram for the recharging of the lead acid cell. Here you can see that lead sulphate precipitate has been deposited on both the electrodes, but when I connect it to the DC supply, then my cathode, the cathode of the voltaic cell, it becomes anode, and the anode of the voltaic cell during recharging process becomes cathode, and the signs are reversed. So, we again get the lead at one electrode, the lead sulphate gets converted into lead, and in the other electrode the lead sulphate gets converted into PbSO4, it gets converted into PbO2. So, the reactions that are taking place on the two electrodes during this recharging process, at the negative electrode, the lead sulphate, it accepts the electrons from the direct current and it gets converted into lead plus sulphate ions. Now, here lead oxidation state of lead sulphate, lead is +2, but here the oxidation state of lead is 0. So, lead is undergoing reduction at the negative electrode, whereas at the positive electrode, the lead sulphate reacts with water in the presence of the electric current from the DC source, and it produces lead dioxide as well as H plus and sulphate ions, and it releases electrons. Since again lead is getting converted from +2 to +4 oxidation state by the release of 2 electrons, so lead is undergoing oxidation at the positive electrode. Now, the 2 electrodes which were converted or which were covered by the lead sulphate, they have recovered to once again act as cathode and the anode, and the overall reaction for the charging is given by 2 PbSO4 lead sulphate plus 2 water. The charging gives lead sulphate. Here it is also using the energy from the external source to give lead solid plus PbO2 plus 4H plus 2 sulphate ions. So, the process has been reversed. Now, the cell is again recharged to function as the voltaic cell for the supplying of the electric current. Thank you.